Right, and so you see this nice drill rig. That's our own institute-owned drill rig, the Borex in German. And I would like to tell you something about the drilling work that we did during the Push It project. And for example, Tom Olver introduced the Push It project already a little bit, and I will go further into details. But first of all, we need to think about how we can access flooded underground mines. And a while ago, I made this little figure here. And of course, we know we can access the mine water to drainage adits or through open shafts, use it for open systems, for closed systems. But then in some cases, the shafts are plugged and the mine water that we want to access is not easily available anymore. So we need to drill. And this can be done in different ways, and this can be done for, let's say, normal geothermal applications, but also for MTES systems. So Push It, to introduce this again, Push It is not this song from the 1980s, you might know. It stands for Piloting Underground Seasonal Heat Storage in Geothermal Reservoirs. And really important is that in the Push It project, the EU-funded project, we look at high temperature heat storage in flooded underground mines. And in Bochum, we have an MTES pilot site. MTES stands for Mine Thermal Energy Storage. And this is quite a nice figure to explain it to the public. So the idea is to utilize the flooded underground mine as a big geo-battery to store surplus heat inside the mine water body and then pump it out whenever the heat is needed. In our case, we have a former colliery, the so-called Mansfeld colliery, which lies directly below the technical center of the nearby university, the Ruhr University Bochum. And at the technical center, there is a data center, there is a CHP unit, and two cooling towers that basically just blow the heat out into the environment. And we thought about, okay, how can we connect the technical center of the university, where we have surplus heat, to the mine that lies directly below? And you can see a scheme here of the mine. These are two parallel galleries, estimated volume about 10,000 cubic meters. An interesting fact, this mine was used as an underground factory during World War II. It lies 120 meters below the technical center. So our idea was, okay, let's drill into the mine and utilize the mine as an MTES system. First of all, we need to look a little bit about geology, because this is quite important for the drilling process. So there, under the technical center at the Mansfeld colliery, we have alternating layers of the upper Carboniferous, and we have a local saddle and basin structure with steeply dipping clay stones. And please remember this, because this caused some challenges during the drilling process. And then we also have interbedded sandstone layers with isolated soft coal seams. Obviously coal mine, so this is why the coal mining was there. And also an interesting fact when it comes to drilling, because we want to utilize the mine with pumps, and we needed quite a large diameter borehole. So in this case, we have 12 3/4-inch borehole. And here again, drilling into the mine 120 meters below the surface. You can see a picture of our drill rig with one of our students in front. It's a Hütte HBR 207 GT drill rig from the German company Hütte. And it's a double rotary drilling system. You can see this here. So the point is that it's a shearing system and not a crushing system. So the cuttings are transported out by the drilling fluid, but it's shearing and not cutting the rock. Here an overall image. So again, for the size comparison, in total the drill rig is 40 tons. And there are PDC drill bits used. And here you can see Stefan. Stefan was here last year or 2 years ago and also gave a presentation about Push It. and Stefan is investigating the cuttings in this picture. So we drilled, and then we did a geophysical logging and a camera inspection. We looked at the well path and did a deviation survey. We proved the gamma ray, or we used the gamma ray tool for the lithological differentiation of the different layers. Then we did AB, acoustical borehole televiewer, to see fractures or joints or faults inside the drilled through rock. Then OB, optical borehole televiewer, really nice. You can see really interesting layers in these images. And we also took samples from the mine water body. And then when we were successful to drill into the mine, I will come to this just now, we saw that, well, this mine water is actually groundwater quality. So 12, 13 degrees Celsius, 850 microsiemens per centimeter electroconductivity, pH value 7, so nothing really concerning. And people always say, oh, mine water, this is really toxic and you need to take care. That's not always the case, and I think this is also something that needs to be communicated. And then we also did a camera inspection, so we were tapping into the mine to see what's going on. It's an image of our borehole camera with the centralizers, so that the camera is not wobbling around inside the borehole. The optical televiewer, and later down in the recorded presentation, you can scan this QR code. This is one of our sampling videos. Here you see that something went wrong. You can imagine what went wrong. Our first borehole was not vertical, and we missed the gallery. Yep, we were drilling and drilling and drilling, and at 120 meters depth, there was no gallery. So you can ask yourself, and you don't really know that before, was maybe the mine plan incorrect, or did something go wrong with the drilling? But we figured out that there was quite a lot of deviation in the soft layers, almost 5 meters, and the borehole assembly was slating away, and we missed the mine gallery. So we had to adjust the drilling process. And how did we do this? We had to adjust the bottom hole assembly, so the big thing on the drill rig. And how did we do this? We used additional heavyweight drill coilers. You can see them here in the picture. And we used a so-called pendulum assembly for stabilization. And it's just a pendulum effect. So you have a heavy weight on the bottom of the bottom hole assembly, and it just keeps the bottom hole assembly straight so that you can go down vertically. And I also didn't really know about it, and you maybe also don't know about it, so I found this really helpful video on YouTube where the lecturer is explaining the pendulum assembly, but that was the solution to our problem. So what are the lessons learned from the drilling? First of all, we were successful the second time, which was really good. So borehole 1 is the red one. We really can see the deviation from the vertical drilling, almost 5 meters. And then in green, it's the second, P2, we just drilled next to it, and we only had a deviation of 0.5 meter. And then also in P3, the third borehole, we were successful, deviation of only 1 meter. And you can see this here, that we were able to tap into the mine. And now we will drill P4 and P5 in May. And I think we know now what to do because we adjusted. And this is a learning process. And luckily in our case, we have our own drill rig, we have our own drilling team, and it's a research project. So we really can make mistakes, but we also learn from the mistakes, and we adjust our system. A few more lessons learned from the installations. So we used wire-wrapped screen tubes with fiber optic cables. And this is also something that is not necessarily done because there are not always fiber optic cables used. But we wanted to see we wanted to know the optimal temperature for the backfilling with the clay cement slurry. Then we also used a crossover top drive, and this is important to connect the casing with each other without using additional pliers. And then maybe the most interesting fact, Usually for geothermal application, steel casing is used. But in our project, we were able to use glass fiber reinforced composite casing. What a word. In our case, from the company Huisman, a composite tubular casing. And the important thing is that it's corrosion resistant. In our case, maybe not so important because I told you the mine water was or is not highly mineralized, but in other mine water geothermal applications, this could be a completely different case. It's lightweight and it has high pressure and temperature resistance. And remember, we are talking about high temperature MTES system. So at the end, we want to inject water with 60, 70, 80 degrees Celsius. So it really needs to be temperature resistant. At the end, this is our team. And if you have further questions, you can either contact Stefan, our project lead, or Jonas, our head of the drilling department, when it really comes to drilling questions, or me about hydrogeology and or the public relation and nice talking stuff. All right, then I would like to thank you and say Glück auf, because this is the German's minor greeting.